Okay. Hey everyone, we are here for our testing session here. So we're going to do a quick audio levels test, check out our stream and make sure that everything is sounding good. And as you can see, we fixed our internet quality issues from last time.
Yes, thankfully. That is very good.
Oh, you can hear. For our testing session here, so we're going to do a quick audio levels test, check out our stream and make sure that it's sounding good.
Is my auto gain on?
It is on, that's why. You're right. All right, guys, we're going to go fix something. We'll be right back.
Last time. Yes, thankfully.
All right, guys, we are back and we are testing once again.
Testing 1, 2, 3.
We turned the auto gain off. There's this very stupid setting in Chrome that tries to control microphones gains automatically, but it's problematic when it comes to USB mics and Yetis.
That's for sure. So this one is going to be a lot better. Testing 1, 2, 3.
Testing
Testing
1, 2, 7, 3,
7, 4, 1,
5.
3, 2. 1.
You're a little quiet. I'm going to turn. Is your gain set appropriately?
The
3.
Yeah.
Is it 3?
Right there.
Okay, testing, testing. 1, 2, 3. Testing, testing.
Testing 1, 2, 3. Testing. Let's see. A little bit of echo. Testing, testing, 1, 2, 3. Testing, testing, 1, 2, 3. Testing, 1, 2, 3. Testing, 1, 2, 3. Testing, 1, 2, 3. There's 4 people watching right now.
What?
Yeah. Hey guys, sorry, we're just doing a little bit of testing.
We're still testing. Give us a second here. Actually, doesn't sound bad. We do need to turn you up a little bit.
Yeah, a tiny bit.
I'm still much louder. Let me turn your. Wait, why are we hearing that?
I reloaded it just to make sure that, make sure it wasn't my connection, but it might be.
Freezing?
Slightly. Let's check the stream status is 4.
Why? I'm seeing good quality on our end, like on the Video Ninja. I wonder if it's my computer up there. I might have to go check. Let me turn your microphone up slightly on this end.
Yeah, I don't think it's our computers at all. Because the quality is really good for me as well. If my Chromebook is running.
Testing.
Testing.
Testing. I turned it up 3 dB, so let's
3
see.
dB. 3 dB. 1, 2, 3.
The compression should be taking care of the dynamic range, but oh, that sounds better. Compression should be taking care of the dynamic range.
The dynamic range. Boom, boom. Yes, mic test. Mic testing. Testing the microphone right now. Test 1, 2, 3. Testing, testing. 1, 2, 3. Real good, real great. Life is good. Life is awesome. We're gonna figure this out.
Everything is awesome.
Imagine your cat messed with the connection again. Found it. Was like, nom 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 nom.
That sounds about on par with mine.
I think it's the connection upstairs.
I
think it's the connection upstairs.
Is the video dropping out?
I think that connection was stable.
Okay, so our microphone levels are good, it looks like. I do need to potentially adjust our, actually, let me just close out this connection real fast. Now that I closed out my connection to my computer, because that might be causing a resource strain, let's do a couple audio test connection or audio tests. Make sure to offset your noise reduction housing, blanking on the name for it, but the make sure to adjust it offset slightly so that it reduces the range at which it can accept.
So where do I want it to be?
So like mine is offset so that right now it's like the range at which it's able to accept frequencies hitting it is going to be about right like this. So you want to, yours would probably just want to, angle it in a little bit. Yeah. Range at which it can accept. So like, yeah, that sounds good. Offset so that right now it's like the range at which it's able to accept frequencies hitting it. It's gonna be about right like this. So you wanna, yours would probably just put in a little bit. Yeah. Are you gonna say anything?
Testing 1, 2, 3. Testing my microphone. Hopefully there is no echo. Hopefully that it is good enough to just talk really nicely and that the sound is good. Please have a good sound. Test, test, test. 1, 2, 3. Testing 1, 2, 3. Testing 1, 2, 3.
Could bring it closer to your face.
And bring it like right here.
Mm-hmm.
This should be able to do pretty well. Hey, that sounds good.
It does sound good. Yeah, I think we can work with that.
Mhm.
You guys want to hear me spot coffee?
Okay, oh wow, that's just beautiful. Truly beautiful. Okay, the stream status is excellent.
Oh, really? So now that I'm not connected to my computer, it's fine.
I think that's what it was.
Bring it closer to your face. That sounds good. Yeah, I think we can work with that. You guys want to bring some coffee? Let's
And go that way a little bit more.
if that sounds any better.
All right, we're gonna do it from this
So
angle.
testing
Testing this out. Let's
see if there's any reflections or inflections,
inflection,
deflections,
uniflections,
unflections,
real flections,
preflections.
postflections.
So testing. See if there's any reflections or inflections, deflections, unflections, reflections. I'm still a little louder, but
Should I turn my gain maybe a little bit?
yeah, maybe turn up your gain. Just don't turn it up to 4, but just turn it up
3.5.
Yeah.
Okay. That should be around 3.5. Hopefully that sounds better. I'm hoping so. Testing. 1, 2, 3. Testing.
We're at 3.5 dots.
Yeah.
3.5 green dots of gain.
Mine's blue.
Or blue dots of gain. Also, did you check your microphone pattern to make sure? I don't think unless you changed it, I don't think it would
Yeah, I didn't change it at all. There's still some like,
some reflection going on.
that might also be the stream from my phone.
No, it could. Well, yeah, it could be, and it also could be that my microphone is picking up more for some reason.
Every time it seems to reverse itself. It's either my microphone's picking it up or your microphone's picking it up.
Mm-hmm. Let me try doing it this way and seeing if that
helps at all.
affects it. Testing.
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 1, 2, 3.
So testing.
What is testing?
Testing. But testing.
And then a test, perhaps.
You know? Whoa, that sounds good. Nope, that's worse. That's worse. Yep, it needs to be this way. All right. Let's do one last round of
testing again. And again and again and again and again.
Testing?
Testing.
Testing.
Testing. Maybe a little bit of testing.
Testing.
More.
I find this very testing.
Very testable. Testicle? Oh, there's that initial like da-da-da, and then it hits. It's almost like the connection is still excellent.
Did you connect with a microphone on that or not?
There shouldn't be. Should say.
Well, that's audio, not a microphone. All right. Let me try one last thing here. And then if this doesn't work, we can always go and get a sound dampener for the floor. Cut out on the reverb reflections.
Ooh. My life be like ooh, life be like ooh.
Can't wait till we don't have to deal with reverb.
I know it's gonna be wonderful. It's really just the complication of the setup, which
Was the environment that we're dealing with. Okay, I'm gonna need you to. Well, first off, let me test here. Test, 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 test,
test
test, test.
testing the microphone.
Okay, now let me try mine. Just mine a little bit. Because when you said something, it reflected, which means it's my microphone that's receiving it.
You can just hide behind it like this.
Don't hide behind your microphone skirts.
I'm scared.
All right, go ahead and say something.
I am saying something currently. I'm going to talk into my microphone very highly or not highly. I speak very highly of my microphone. It's good, but
No, I speak highly of my microphone.
both our microphones.
My microphone.
Wonderful.
It's better.
It's better.
I'm gonna increase this slightly. All right, testing, 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 testing.
1, 2, 3. Testing the microphone. Testing the microphone. 1, 2, 3. Testing the microphone. There's that small amount. It might be
Try this. Testing, 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 testing. 1, 2, 3.
testing. 1, 2, 3. Testing. 1, 2, 3. There was nothing there.
Yeah, I
So,
didn't hear anything there.
yeah, that sounded really good. I'll just make sure to be very close to my microphone, like this.
I don't want you to have to do that for there to be no, because that's not going to be a perfect solution because you're going to forget when you get caught up in talking.
Yeah, that's true.
Plus, it's an added stress, but I made a modification here, a slight modification.
Very slight.
That increased the quickness of the gate release here. Yeah, that sounds great.
Yeah, I like it. We ready?
Okay, yeah, let's turn that off. And then we will go to our loading screen and be back shortly.
Alrighty, guys. See you in a second.
All right, and we're live.
Hey guys, welcome to ThetaWave Podcast. I am Jacob. I'm a neuroscience researcher, as well as someone who's very interested in machine learning and as well as various other topics. And I'm here with my co-host, Ryan Reed. He is a machine learning expert, singer, songwriter, and potential playwright. So, Ryan, what have we got going on today?
Well, we've actually got some fascinating topics. We are going to be going over Oxiracetam as our nootropic topic of the day.
It's going to be pretty awesome.
Which is going to be fun. That one's got some pretty interesting research behind it, and is somewhat similar actually to in the way that it works to the Nephiracetam, which we already went over. And then we're also going to be going over our machine learning topic is going to be reinforcement learning as a whole, which is going to be fun because that's got some kind of fun concepts behind it.
Oh yeah, definitely.
And some parallels between us, the way that our brains work, or some more obvious parallels between the way that our brain works and the way that it works, which is fun. And then we are going to be going over as our neuroscience topic. Remind me, what is our neuroscience?
We're going to be going over the hippocampus.
The hippocampus, correct. Okay.
Yes. And I think this podcast, we should start with reinforcement learning. I think that would be a great thing to start with, and then go into the hippocampus.
Really?
Personally. Yeah. Switch up a little bit. We did neuroscience last week. Let's do machine learning this time.
Okay. All righty. We can do that.
If you're down.
So I was not prepared for doing this right off the bat.
Ready? I'll put you on the spot. Let's see how much of an expert you really are.
All right. So I guess to kick things off, we will examine the differences between what reinforcement learning is and what deep learning is. Because actually, before we get started, let's just double check our audio, make sure that we're not going into all this for nothing. Okay, we're good. All right. So to understand kind of the differences between reinforcement learning and typical deep learning, we first need to understand that there is a difference between them because they are different architectures. Typical deep learning is what you see being used in things like ChatGPT, as well as diffusion for image generation. Pretty much almost all of the applications that you think of when you think of machine learning are built primarily off of deep learning. Now, that's not to say that there are never reinforcement learning components built into them. A lot of the overall applications have reinforcement learning elements built into them, such as Gemini, I believe, has a reinforcement learning element built into it.
Now, let's reverse that real quick. Do some reinforcement models have an aspect of deep learning to them?
That's a very interesting question, just in the nuance of what you're asking. But yes, it's more common to see deep learning have a supplementary reinforcement learning network because deep learning is the primary architecture used for AI tasks, right? And so it's more common to see a reinforcement learning component built into a deep learning architecture than vice versa. But it really just depends on the purposes and the goals, which we'll get to in a little bit.
Yeah.
So we'll start off by kind of examining their individual purposes for those architectures. With deep learning, its primary purpose that you see it used for is to make predictions. Deep learning is designed to find the optimal network configuration to be as accurate as it can in its predictions across inputs. So it's really good at learning to predict across different sets of input data. And that those inputs, those predictions that or those outputs, those prediction outputs that it gives can take a lot of different shapes. They can be classifications. They can be forecasts, such as with LSTMs. They can be fundamental features of something. They can be future time step projections.
Yeah.
But the main universal component is data is input with the goal of predicting data as an output, right?
Yeah.
So reinforcement, this is where reinforcement learning kind of differs here, because with reinforcement learning, the primary purpose is to take an input with the goal and use that input to determine an appropriate action to take based off of it.
Okay.
So its goal is not to make predictions about future data. Its goal is to make a calculation, a prediction about the best action to take given a set of data.
So
now, go ahead.
Let me just make sure I'm getting this straight. Kind of like how it's a classical program, you have the rules, right? And then you have an input, and that is supposed to generate an output. But with this, it's more so, it's configuring the rules itself to find a way to learn how to get to the output you've already decided.
Yes. So yes, it's without oversimplifying.
Simplifying it, yeah.
But yes, and you'll kind of see how that all comes together in a little bit here. The common thing I could think would kind of pushing back on the previous statement of it predicting its purpose being to predict actions. The pushback there from someone that might be, well, why couldn't that just be done with deep learning? Couldn't you just predict the appropriate actions, and train the model that way to predict, the appropriate.
Yeah, it seems like all it needs.
Appropriate actions. And you wouldn't be entirely wrong, because you can do that. But it's the kind of a fundamental approach to that differs and makes it reinforcement learning more suitable in many cases for learning actions. So to understand this, we'll take a kind of a little bit of a deeper look into the architectures, because deep learning in a broad sense takes an input and uses a reference. You can think of it as like a cheat sheet or an answer key, and tries to figure out how to transform that input to match the output. And it does that across a broad range of inputs and outputs, and tries to configure its network to be able to match all the different answers as well as it can. One of the key components there that allows that to be possible during a section of the training called backpropagation is the loss function, which the loss function basically is a function that calculates how far off our network's predictions are from their goal prediction or the answer key. So, so we calculate on average how far off our predictions are. And you might think, well, why don't you just calculate the difference between the two, and you could be in a very simple network. It could be that simple, but you have to consider the fact that you're not always dealing with one input and one output. You're dealing with multiple outputs, potentially even multiple time steps with multiple outputs, and then multiple batches with multiple time steps with multiple outputs. And so you have to figure out what the best way of appropriately determining how far off something is. And it's not even as simple as that either with the loss function, because sometimes it's not just a matter of how far away something is from something else. So if I were to, for instance, if I were trying to make a trade prediction, right? If I were trying to predict trade data, and I were to say, my model is $10 off from the target price. What does that mean? Is that good or bad?
Bad.
You sure?
Is it a good thing that it knows that?
Is it a good thing that it's $10 off, or a bad thing that it's $10 off?
Probably a bad thing.
Are you sure?
I would say. That's my guess.
But what if the target price was $12 and we just predicted $10?
Then it's pretty
That's
close.
fairly good. That's closer.
Yeah, that is good.
What if it was $10.50? Like that's really good.
Yeah, that's really good.
But if the target price is $1,000, that's really, really bad.
Yeah.
And so loss functions help account for things like that, where it's not just a matter of simple differences, and we scale the inputs typically too. So we take that means that we take all of the big numbers and put them in a range between 0 and 1, or like -1 and 1. And so that changes things as well in the way that those loss functions handle the input data.
Mm-hmm.
And sometimes you want to kind of logarithmically calculate errors so that it's more obvious the more error that there is there.
Yeah.
And so there are a lot of, and those loss functions become really important in the way that they calculate it, because then that determines how much the optimizer then adjusts the network to correct for those errors.
So both of those are kind of working in conjunction together to better tune the model to be less wrong.
Exactly.
Okay.
And so that was way too much detail for what I was the point I was getting at there. And I apologize for that. But
we like to get technical.
The basics of it is that we use the loss function to calculate how far our predictions are from the answer, right? Mm-hmm. That means we have to have the answer in order to make that calculation.
Yeah.
Reinforcement learning doesn't need the correct answer for an input to make a prediction. Instead of a loss function and a reference, it uses something called a reward function.
Oh, yeah, right.
And another term for this is its policy, which is essentially a function that evaluates the outcome of a chosen action and rewards or penalizes the model based on that outcome. So it's evaluating arbitrary outcomes, not accuracy. And so that's essentially how the model is going to learn, and how its weights are going to be adjusted, which leads kind of to the key difference. Reinforcement learning models are models designed to achieve specific goals, whereas deep learning models are designed to predict a specific answer. And this is also why reinforcement learning models are great at playing games and are often used in robotics. because of its ability to account for nonlinear, no right answer environments.
That's that seems to be very much like how the algorithm behind our emotions also works, because oftentimes there isn't a definite outcome, but we either have a negative or positive emotion associated with that experience to then further inference into how we should act. And if it's a successful positive one, then we'll continue to do that. So it's very similar in that way, which is really cool.
Now, if you want to delve into further how it actually achieves that, it's going to vary depending on the algorithm chosen for the reinforcement learning model. And so there's an element of variability across architectures and across algorithms. However, it all started initially with the Q value function. So to better understand that, it helps if we go over a brief history of reinforcement learning.
Let's do it.
And take a look at kind of where that architecture came from. Because, it's not just like an AI got up one day and started playing Atari or chess and was able to beat somebody,
Is it, can I turn down the fan a little bit? Because I am chilly. Just like,
sure.
All right, sweet. Also, the auto director's not working.
Oh, I forgot to turn it on. That's why.
Oh.
All right. In a second, we are going to go over a brief history of reinforcement learning. But for the moment, you'll receive Ryan's answering machine.
Yes. Oh, that feels so much better.
Let's get that auto-director auto-directing.
Auto-direct.
Auto-direct. Call auto-direct today. Oh, Riley. Auto-direct.
Auto-direct.
Okay. Get that minimized. Get that brought up. I'm glad you reminded me of that.
Yeah. I was waiting to get into a good place to where we can stop and turn that on without you having to refine your flow.
Appreciate that. Okay. Should be on. You want to double check that for me and make sure it's indeed auto-directing.
Yep.
That would be perfection. Once it kicks in. Kick in. Come on. Come on, director. Direct me.
Come on. Let's do some direction. Let's see it.
I want to see you directing.
Direct it.
Direct.
This will be cut out of the video. I'm so excited to be the one to do that. Honestly, I think it would be fun if we had the whole podcast edited by tomorrow. It's like you step me through it and we finish and upload it. That would be pretty awesome. Come on, auto direct. Nothing showed up yet.
Weird. Oh, there we go. I think it might be working.
Might be working.
Change something here. Testing. 1, 2, 3.
There we go. Now it's on.
Boom. Alrighty.
Heck yeah.
Okay, guys. Now we can take advantage of all of our cameras.
Yes. All of our AI cameras. Thank you, Dave.
Thanks for your patience there. All right. So, where were we?
History.
Yes, indeed. History. So reinforcement learning has its roots in human psychology. And what is the earliest reference that you can think of to reinforcement learning as a term or concept?
Reinf- Probably like is it the Turing machine?
No,
No, what's that?
that's AI. Well, that's a programming, not so much AI.
Okay, never mind.
It's the first instance of a computer.
Oh,
in
that's
its
right.
modern sense.
I mean, if I were to guess, I would say that it probably originated in maybe around the 1950s.
You're not far off. There was a lot of developments during that time.
That's when
But the earliest occurrence of reinforcement learning actually started with Thorndike and his work with animal learning. And he created something called the law of effect, which basically states that a action followed by a positive reward would lead to an increased occurrence of that action. And which kind of seems pretty basic, but it essentially kind of laid the foundations for reinforcement learning and a lot of the other research on that would come later.
which is actually really cool because that law of effect has become very mainstream. There's a lot of people talk about it, but they don't know its origins. They definitely
That's
should.
true, yeah. And reward and punishment, it's kind of like that foundational element there. And Thorndike, his work in the late 19th century and early 20th century kind of paved the way for that. Then in the mid 20th century, we see development of things like optimal control theory, which essentially was a bare bones mathematical framework for designing a system to make the best possible choices for a task, such as guiding rockets and other things like that. But it still isn't at this point, it isn't the system that we recognize as modern reinforcement learning.
Yes, but this was kind of like the start of it.
Right. These are a lot of the foundational elements that kind of led to it,
Kind of planting the seeds a little bit.
To get to what we would recognize as modern reinforcement learning, we first have to cover the developments made by Richard Bellman in the 1950s when he
1950s.
Yep.
Too far off.
When he first created dynamic programming. This was basically done as a way to solve complex decision problems by breaking them up into smaller mathematical chunks and essentially pre-planning things to account for eventualities that may come up, So after that important development, there was still kind of a major challenge and hurdle there. Real world problems are hard to account for and have oftentimes immeasurable potential eventualities, and if we consider, kind of a very basic problem of a robot having to navigate a room of people, there are countless paths and variables, like paths it could take and variables that it may have to account for. And I don't know, like as examples of that, you have where people are in the room, how fast they're moving, what their orientation is, what their likelihood of continuing to move will be, where people were, where non-moving objects are in the room,
as well as where they are in relation to those objects.
Exactly, where they are, as well as their boundary, exactly, and their orientation and their travel paths, as well as potential unaccounted things that they don't see, like person behind a person that may happen.
Oh, yeah. Unexpected variable. Calculate that.
And so there's just like so much that could potentially happen in the realm of possibilities, you know.
Yeah, no, seriously.
And so you have to figure out, how do we deal with that kind of thing? And that's kind of what led to the huge breakthrough, and where that comes into play, essentially, was the development of something called temporal difference learning, and then the Q value function. So we'll start with the Q value function, and explain kind of what that is. We can think of the Q value function as essentially a best guess at an expected reward that will be obtained by taking an action in any given situation. And you can imagine the Q value function used at every step in the process as new information becomes available to update its beliefs about the environment, and as a result, its likelihood of obtaining a reward given any specific action. So it's constantly, the Q value function is something that constantly updates as new information becomes available to determine likely rewards based on the available actions that can be taken within that context window. So that's where the whole temporal difference component starts coming in, because it's not just about what happens now, like the outcome of the current action. It's about what happens later on.
So let's say there's somebody that it recognizes in a room, and it sees a hand reach out behind it and a little bit of a shoulder. Is it then going to recognize that as a potential other human being, and then come to the conclusion that there is another person behind that person, and then is able to update its information? It's constantly trying to like predict what's coming next.
If you were to really, really, really oversimplify it, yes. But in actuality, what it would probably, if it got enough experiences with things like that becoming a problem and it's navigating its environment, what it would learn to do is recognize that as an unaccounted variable, something that it didn't know what it was going to do. And so that would factor into its decision making. And so it wouldn't necessarily recognize it as a human, another potential human. It might recognize it just as a potential problem variable there.
Now, is it then going to associate with it in a way that accounts for that unexpected variable? How does it account for it?
It's basically going to, if there's enough instances where that kind of unaccounted variable, for instance, a hint at something else that is unseen, becomes a problem, then likely the network would learn that that is a relevant factor when choosing the appropriate route to take. And supposing that there is comparable routes that you can take, then that would lean weight towards not choosing one route over the other. And so it's those really complex decision-making things that it starts to learn, those elements of why. I don't know if you ever thought about, like, why do I decide what I decide?
Yeah.
And why do what were the components that influenced that decision that I made? And
think about that way too much.
Probably me too, but yeah. Reinforcement learning is the formulation of those components that influence those. That's why we call it a Q value function, because it's learning a value or it's learning multiple values. And through those values, it's determining or I should say, it's learning a particular primary value and then supplementary values. But through that value, it is learning to make those decisions.
Yeah.
And so with that goal-based behavior, really like simplistic kind of example, if you were trying to train a robot to get to the other side of the room, the end goal, a simplistic example of that would be that the fastest that you are able to get to the other side of the room without touching anything, then the higher your reward would be, right?
Mm-hmm.
And so given any specific environment, it would try and figure out what the fastest route of getting to the other side of the room without bumping into anything would be. And that would be its value, would be the getting to the other side of the room as fast as possible. And that's kind of like a really trivial, simplified example of something, but like you can think of it kind of like that's what we're, what we're saying there is, your primary value and then your optimization along the way. And, with Q value and temporal difference learning, the Q value led to temporal difference learning, which is basically just an extension of that. But temporal difference learning adds the component of calculating rewards over time, not just immediate steps. It's not just about, okay, what step is going to give me the most immediate reward. Is projected. If I do this, this will maximize my reward. And if I take this action, this will maximize my reward in the future. And optimizing the maximum reward every step that it takes, to try and get as much reward, as it can. And so that was kind of the key component there, because it brings it from a immediate action reaction thing to a more of a future projected action based decision making, which comes with significant benefits, because it's not just a correcting problems as they arise, it's avoiding potential problems before they ever happen.
I see.
So essentially, the Q value function allows us to learn by comparing its chosen action or actions taken with the actual reward received. And so that's its version of back propagation, where it keeps track of the action it chose and the reward that it got for that action, and evaluates the basically kind of in the same essence that back propagate updates a network after determining how far off the loss was there. The Q value function allows this back propagation by determining how far off its predicted reward was from the actual reward that it received.
Okay, so let's give a scenario here. So let's say you give the robot a task of going around the corner and opening the door and going in the next room. When it goes around that corner, it meets an unexpected variable. The door is not there. What there is a sign that says the door is right behind you. And this robot has a general concept of what a door is, what a wall is, what words are, what a sign is, what direction behind means. And even though it came across an unexpected variable, would it be able to then learn and understand that the reward is in another direction? Or would it have to take a lot of time for that to update because of the error?
Likely in a simple network, a simple reinforcement learning network, that would take an incredibly long time, as well as an incredible amount of noise put into the network. So actually, I should further explain that to answer that question. But we oftentimes will you run into if you in reinforcement learning as its kind of native architectural self, you end up running into an issue where a robot will start taking actions that it learns initially, that give it better rewards, and will never start trying to find more efficient methods of that. Okay. And there are various ways of dealing with that, one of which is introducing noise into its data and decision making, and kind of giving it you can think of it almost like a random chance of prompting it to choose a different action. And so it forces what is called exploration, which allows that even if it finds a good path, occasionally it will make a choice outside of its comfort zone in order to determine if there's a better path.
Okay.
And so, because we don't just want to find a good path, we want to find the best path.
Yeah.
And so if it takes an action and there is, during its exploration, and it gets the hint that there might be a better route to take, then it might start exploring that as a potential possibility, so that's oftentimes what our in a more complex manner, what our brains do.
Yeah.
There are variables which prompt that exploration that we don't have in reinforcement learning networks, but it simulates that component of humans where it kind of prompts the urge to explore and try new things. And so, were you to choose the right architecture and base architecture, properly model your reward function, and introduce a level of exploration, it would eventually figure that out. Yes. This is also one of the problems that can come about with training reinforcement learning models sometimes, is that they can be very hard to train. Like they require the very specific setups and parameters, and oftentimes, in order to train them efficiently, they require very, very specific setups and parameters. And if you don't, sometimes even if you do, it takes them a long time to figure things out depending on the complexity of the scenario. And if you think about it, that makes sense. It makes sense that would be the case, because they're not just doing what normal deep learning does. They're not learning from an answer key. They're not memorizing facts like students do.
Yeah.
They are dealing with unaccounted, innumerable variables and trying to learn how to navigate life despite those variables changing all the time.
Yeah.
And so there's just so many possibilities for them to deal with and account for, that it makes that training process really, really intensive,
Yeah. Because thankfully for humans, we have very complex pre-programming that allows us to fully maximize our navigation in the world. And so even though it takes a very long time for people, the results are wonderful.
And if you think about it, we have, and we've actually learned to develop this as well into reinforcement learning models. We have something built into us called the, I don't know if this is the appropriate term in the biological equivalent, but in reinforcement learning, what is called is imitation learning, and is basically where a network learns to do by observing somebody else doing it.
Yeah.
And so they start off, they basically get a head start on learning something by observing somebody else do it. And then they tune and fine tune their own ways of doing it according to their own environments. And so that's a very fast way of, if you have an example or can, like if you wanted to teach a robot to move, rather than having it have to figure out how to do that from scratch on its own, a better way of doing it would be to watch you, supposing it's a bipedal robot, would be to watch you move and try and imitate that. And that would give it a head start on its learning and figuring that out.
Yeah.
And then you could have it tune its own movement based off of its individual, size and bounding box parameters and all that kind of stuff.
Yeah. That's really cool.
But so anyway, the Q value function allows a model, which in reinforcement learning we refer to as an agent. It allows it to learn the best strategy without needing a complete map of the world, without needing to know all scenarios. Essentially, it allows it to operate in a dynamic, ever-changing, and imperfect environment, which is where its key. One of the reasons that's where its key benefits come in. Deep learning inherently doesn't like outliers. Reinforcement learning inherently learns to account for outliers. And so we want to take a look at kind of practically what that looks like in an overarching sense in modern reinforcement learning, or modern deep reinforcement learning as it's currently typically worked within. I can kind of go into what the different components that make it up typically are called and what they do and whatnot. We won't go into detail and all that stuff because of timing and just the fact that there's way too much information. But we can possibly go into that stuff in a future video. And kind of, but for now we can kind of get a high level overarching view of what the different components are that are used to make up this, this network. You have in reinforcement learning, you have the agents, which is also sometimes known as the actor. That is essentially the model that is responsible for making decisions. And it is the algorithm and architecture chosen to learn how to navigate the environment given a specific, reward function. And so what happens is you have an agent or an actor, depending on what you want to call it. Then you have an environment. And an environment is basically you can think of it as a specified overarching setup that defines the places that you can put the variables. So let's talk about in the context of me. What would your environment be? Your environment would be your visual snapshot, what you could currently see, what you could currently hear, and what you currently feel. Those sensory inputs make up what you know as your environment, right?
Yeah.
And those components, and I should specify, those components that you can interact with around you in those ways make up your environment. Now, beyond environments, you have states, which is the current state of the environment and of the agent within the environment. So it's your current state and the current state of the environment around you. So where are you? What is your position? What is your orientation? What are the environment variables around you that you can observe, feel, see, hear, whatever. And so that makes up a current state. It's the you and the environment. And so with that knowledge, an agent makes what's called an observation. They make an observation about a state within an environment. That makes up a single decision, is going to be an observation about a state within an environment. And that is the information it uses when trying to calculate its next action and the action that will bring the appropriate reward. Now, this is where that reward function comes in and becomes very important, because how you reward those actions determines how that network learns and adjusts.
Mm-hmm.
So if you want it to gain a higher reward for more long-term actions, you need to adjust your reward function to account for that. So if it has been, and there also, I should state that there are several different types of environments, and you have I'm blanking on the name for one. I think it's static and discrete variables, variable environments, which basically just determine is there a limited number of outcomes, a limited number of actions that can be taken, or is there an unlimited number of actions that can be taken?
Yeah.
And so in the context of a discrete environment, which means that there's a continuous amount of actions that can be taken, that means that every step it has the chance to take any given action it chooses, and your reward function has to choose how to reward those. So if you were to reward actions that happen right after other actions that bring a positive result, the model would learn to make short-term decisions.
Mm-hmm.
If you were to place a higher value on actions that were further spread apart from previous rewards, it would learn to make longer-term decisions.
I see.
And so there are times when you're going to want to tune that, and then times maybe where it won't even matter. But there are factors that you have to be aware of when you're designing that reward function. And a lot of it comes down to the way that you design that reward function.
Yeah.
If it's appropriately reflects your own goals for the model, then it will most of the time figure out a way to navigate towards that goal.
Yeah. Like if you program a robot to navigate a room and you then try to put that same robot in a car to drive it, it's not going to understand.
It's not going to navigate that well at all.
So,
that's going to be pretty disastrous for a lot of people.
Yeah. So the reward function for that would not be correct.
Right.
So it's very specific to what you want that to do.
Which,
But you can
begs an interesting question. Like, it would be interesting. Here's a thought. I might have to experiment with this.
Okay.
Let's
hear it.
I want to create a reward function in a network that learns to create other reward functions that get evaluated against its primary reward function.
Yeah.
So that it can figure out other reward functions that are more specific to specific scenarios. So in that instance that you just gave me, you could have an overarching reward function, and maybe it initially learned how to navigate a room, but it could also develop another sub-reward function on its own that would learn how to navigate within a car.
Yeah.
And could a reward function that would be better suited to that environment.
And then you can have these very generalized rewards for many different tasks at that point. And you would obviously have to teach it.
Exactly.
But if you could learn through observation, you could do it very quickly.
So and that's why whenever we're training reinforcement learning models for things that involve valuable equipment, we typically train them within a simulated environment.
Oh yeah.
You don't want that thing to be training in a real world environment.
You're not gonna put a robot in a Bugatti and be like, all right, you're not
gonna put it behind a freaking semi trailer and have it drive down the road repeatedly until it figures it out.
Yeah, that would not be very good. But you can simulate that experience.
Oh yeah.
You do very well. I mean, that's what they do for self-driving cars. And it's great.
Yeah. It's the kind of the thing that makes reinforcement learning so understudied and underdeveloped is that people haven't yet realized the practicality and the value of it. Oftentimes, like there's a lot more value than in its incorporation into things than is often realized. And it does almost require that there is an action that needs to be taken, because that's what it learns, is actions. But think of the last time that a machine learning model was developed that didn't have the intent of leading to actions in some form or another.
Yeah, exactly.
And so there's a lot of different applications if you just think about it, in a creative way. And beyond that, we consider the introduction of some of the stuff that we've talked about before that can help with the connection between those two architectures, such as the Bayesian probability components and whatnot. That can lead to a better integration of those two architectures. And really, in my opinion, I will say people are welcome to have different opinions than this, but this is a fairly informed opinion. In my opinion, those two architectures, there's no need for those two architectures to be separate. They should be able to be operated and used kind of almost interchangeably. They are different ways of going about it, but they're similar enough that they shouldn't be developed separately. They should be developed together.
Yeah.
If that makes sense.
I feel like they should always be interacting.
Yeah, like we should treat reinforcement learning the same way that we treat different layer and architecture types within deep learning. in the sense that there's a time and a place for it, and it's often beneficial to incorporate it into a model, but it's not always necessary.
That makes sense. Not always necessary.
But yeah, anyway, that's kind of an overview of reinforcement learning. It's super fascinating stuff. And in fact, fun fact, reinforcement learning is one of the specializations that I am currently developing and going into. I've always found it really fascinating. And so the reinforcement learning area of machine learning is kind of one of my passions.
Yeah. I mean, you can tell. Seems like you know your stuff. So bro thinks he's a machine learning expert or something like that. I don't even know. Crazy.
But why don't you tell me about the hippocampus?
Ooh, all right. It's time to get into the hippocampus. I'm actually really glad that you picked reinforcement learning, because there are so many aspects of machine learning that correlate so well to the specific functions of the hippocampus.
Oh, yeah, I could imagine.
Oh, it's insane, because there are spatially selective cells that are used for defining everything that we discussed: boundaries, your relation to objects.
It's about boundaries.
Yes, you always want boundaries.
Establish boundaries.
I mean, genuinely, that is the first thing we do as a newborn. Is before we do anything else, we establish boundaries between things, physical objects, things. Like the first thing that we realize is that we can't go any further in an environment, or we maximize how much.
So spatial navigation.
Yeah. So spatial navigation is one of the first things we learn that is not pre-programmed within our genetics. So things like verbally expressing a cry when something is newly born, that is something that is kind of pre-programmed within it to express its discomfort. And then it learns over time through this very long process of developing an understanding of an environment. And then what it does is that it takes those specific instances where you have a correlation between an object and another object, yourself and another boundary where you can go. And it takes that, and then it takes the abstract notion of boundaries and then generalizes it for multi-purpose use. So if you're in a square room for a while, you are still going to recognize a triangle or a diamond or a hexagon room. You're going to take the abstract notion of a room and be able to apply that to pretty much anything else. So we can even take something like a kitchen, right? Let's say you're a kid who has really never gone to anybody else's house, and you learn how to navigate a kitchen. All right, you can see where the oven is, where the ingredients are, all the drawers, where everything is, what you need to make whatever food that you need. And this is the only environment where you have ever seen a kitchen. What would then happen if you go to another kitchen that has a completely different layout? Thankfully, what's wonderful about the hippocampus is that it takes the raw information that it receives from the entorhinal cortex, and it specifies the value of specific objects or information.
So the fundamental features of the information.
Yeah. So
like in the instance of a kitchen, we would be talking about, okay, this is a stove. This is a primary object. This is something we use to make food, and it heats things up. And underneath the stove, there's an oven, and the oven is also used for heating things. So that's an important component. Then we have cabinets, which seem to hold a lot of different stuff. So those are kind of their own overarching conglomerate thing of just cabinets as stuff where stuff goes. And then, we have the sink, which is not used for cooking stuff. That's used for cleaning stuff. And so that's another kind of component and feature within it. So you start establishing the segmentations of features in a way that then allows you to be able to connect and translate to other environments.
Exactly. And that is thanks to Hippocampus. And it does it very well. You can practically navigate, once you see your specific kitchen, you can navigate any other kitchen and be able to be successful in cooking the relevant food that you want. And let's go into the architecture, a little bit of that. So there are these wonderful things called grid cells. And these are what define your environment and your spatial awareness of them.
A grid cell. I've actually don't know if I've ever heard of that before.
It's really cool. So if you take a rat and hook it up to an EEG and you put it in a new room, as it navigates the room, these cells activate and it starts to form a hexagonal firing pattern around the room that defines the boundary and where it is. It's really cool that it does that. So that's kind of the basic understanding.
That's cool.
It's really awesome.
Huh.
And I wish I knew a little more about that, but that's pretty much what it does. It's pretty awesome. And then you have all of these other cells. You have boundary cells, define boundaries. You have object vector cells, which define your distance between you and another object and where you are in relation to that object as well as other objects. So, it's very interesting. For a long time, I kind of had this weird understanding of neural firing patterns. I didn't realize how many there were that were going off at the exact same time. There are millions and millions of all of these different cells in your hippocampus that are firing rapidly, pretty much at all times, actually. It's why our brain needs so much energy.
Juice.
Yes, because we are so excellent at being able to spatially navigate environments and define our relationships between them. And we do that through observing different behaviors, usually from the people around us. And then we act according to our observations and then associate a negative or positive reward based on the reactions that other people get, as well as your understanding of what it means to be successful in that particular situation. And so one of the things that plagued neuroscientists for a while was, so it seems that the hippocampus is absolutely vital for our spatial understanding of navigation. And it really is. If you look at taxi drivers, their posterior hippocampus is far...
So your posterior is showing.
Yes. This posterior is far larger because that's the place where it deals with spatial navigation, and the interior hippocampus is a little bit smaller. And so there's obviously there's a nice big place in the hippocampus that is related to spatial navigation and what you need to be able to navigate complex environments.
We can almost think of the hippocampus as a dynamic environment of different encoding cells of different types that will start creating these different cell types that are capable of containing and encoding information depending on what is commonly used and needed. And so spatial navigation, there'd be a lot of grid cell development.
And what's really cool is that these, as you interact with new environments, they create a lot of noise, a lot of firing patterns. And what's really cool is that in sleep, the hippocampus recreates these neural firing patterns to better integrate that information back into the cortex, which is awesome. That's one of the main components of sleep, why we need it so much, is because it gives the hippocampus a chance to go over the information that was received in the past day and find the most relevant firing patterns that were associated with a positive reward.
Yeah. We've, I think you and I have talked about that in the past, as how essential sleep is to encoding within the hippocampus, because, it allows for, and this is, interestingly, guys, this is one of the reasons why we have such weird dreams sometimes, is because what it's doing is not only trying to find the most relevant and accurate pathways to use for processing information, but it's also trying to find the most fundamental features. So it's refiring these pathways that have fired during the day with different levels of information or different informational components, added or subtracted from them, and seeing what the outcome of that is to determine what those essential features are, so that it can reduce it down and thus better integrate it into its system and make connections with other things, because the less complex that is, the more connections it's going to be able to draw. And so we have these like really weird dreams that just seem so detached from reality, because we're trying to, our brain is trying to make that determination of like what information there is actually critical to the fundamental structure of this thing.
And what's awesome is that even very simple brains, like in a rat, are very good at this. One of the first scientists who kind of figured out this idea was this guy named Edward Tolman. He was a neuroscientist back in the early 1900s, and he was doing experiments on rats in mazes. So pretty much what he would do is he would start off the rat with one path that had a right direction, and it would find the cheese, the reward. And it would have it run through this only one pathway maze that would get to the cheese every time. So it would go forward to the right, over and over again. And then it would put the rat in an environment with 10 options that it can go in. Now, what's it going to do first? It's going to go towards the front one, the one that it's most familiar with, that it associates with the reward. Now, what happens when the cheese isn't there? It's going to reevaluate where that reward is, and it's going to go back. And now this rat has to make a decision.
It's going to be like, oh crap, I must have made a wrong turn somewhere. Wait, there's only one turn. Where could I make a wrong turn?
Exactly. So once it realizes there are multiple options, well, what do you think it's going to do? Well, at first, you might think, well, it's going to choose the most similar options to the first path. So it's going to go to the second path. But actually what's really cool is that Edward Tolman realized that brains have something, even very simple ones, have a cognitive map. They're really good at spatial awareness. So what is observed is that instead of going towards the second path, they'll go towards the path that is most correlated with that right direction. And so instead of going to the second path, it's going to go to the fourth path instead, because that's where the cheese was spatially in relation to the beginning starting point. It's pretty awesome.
Wow.
To be able to do that. And so in the mammalian brain, this is something that we are exceptionally good at. So even if it's observed in simple rats, we are able to do that in a manner that is far more complex and is able to help us more logically navigate where things are in relation to the physical world. And you might ask, well, we're talking about this kind of goal-directedness, this reward called the cheese. And then we have a physical space.
All about the cheese.
All about that cheese, These rats are even trying to get to the moon, man. It's crazy. They're building a rocket ship right now.
Everyone knows the moon is made of cheese.
Yes.
Did you ever see Wallace and Gromit?
I've heard of it.
It's like a little clay animated TV show that were kind of creepy, actually.
Most of them are.
Looking back at it, but it's like this stop animation kind of thing of this guy Wallace that talks like that, and his or no, was it the guy? No, the guy was Gromit, I think, and the dog was Wallace. Or it was I don't remember who was who, but there's this one episode where they, like, every episode they come up with a crazy invention of some sort, and usually things go horribly wrong. And so one episode they decide that because everyone knows the moon is made of cheese, they're going to build a rocket, go to the moon, collect the cheese from the moon, and then taste it, try to find the best cheese possible, and bring it back to Earth.
Yeah.
And of course that goes horribly wrong, but
of course. Yeah, we're gonna have to watch that one.
Everybody knows the moon is made of cheese.
It's true. But anyways, back to what I was saying is that once it goes back, it has to reevaluate what it's going to do. And one of the ways it does that is through this abstract notion of this temporal understanding of what it could, or a physical, or sorry, a representation of the physical and spatial layout. And it takes these abstract notions of what it can infer to make the best decisions. And you might ask, okay, well, there seems to be a couple processes going on. There seems to be a physical representation of something, the actual environment that it's in, as well as the mental representation of reward. And how does the hippocampus actually encode those two together? Those seem to be almost completely separate things. How is it able to do this at the same time, even in very simpler brains? Well, something that can be represented mathematically. And this is what we've come to know as graph theory. And it can be described as, so structural brain networks can be described as graphs. So with different nodes or vertices that are denoting the natural elements, so like the neurons in the brain regions that are linked by the physical representation of connections, so like synapses and axonal projections. And so you might think of the brain, or sorry, the hippocampus, as this kind of doing multiple things that is able to navigate spatial instances as well as figure out mental representations. What's actually interesting is that we call the hippocampus, the main component of memory, right, and memory processing. I like to call it the main place that interprets information. So it's information interpretation. And this is because they're actually...
Wait, say they what about the information processing? What? Say the beginning of that again. What about information processing?
So
you said most people think
of it as memory processing, right? That's kind of the more general term.
The hippocampus?
Yes.
Okay. I'd say that I don't know. Hopefully people don't think that, because the cortex is information processing. But go ahead.
Or I should say memory. What would you call it then?
Memory encoding?
Encoding. Okay. Yeah, that's really what I meant. Is they call it memory encoding. And another way to look at it is information interpretation. So there actually is only a mental representation of you in relation to the most important information, and interprets it based on past experiences. And it does this through this mathematical representation of graphs, and then connects these nodes together based on the most important information, if that makes sense. and then
fundamental features.
yeah, fundamental features, and then correlates that with abstract notions that you then use to navigate these physical spaces. And so it's practically all mental, and it's interpreting the information that is then used to navigate in the world around it, which I think is really cool.
Yeah.
And so there's kind of a really cool mathematical representation of it. And so, yeah, so it's combining together physical and abstract places into one kind of mathematical connection called graph theory. And there's also place cell theory. So the place cells, they encode spatial locations, but they are also suggesting that they could also be involved in representing numerical concepts by creating a mental number space that then works in conjunction kind of with this more graph theory that is able to have a very intricate and well-made orientation that is very logical, but is kind of a lot like reinforcement learning, just on a more complicated and diverse level. So that's kind of what I find really fascinating about the hippocampus are those aspects of it. Can you think of anything else that might be important?
Well, one of the areas that I was looking into recently with the hippocampus was just regionally where different types of information is stored, in there, and if there's actually been much research to try and segment that stuff out, and turned out that like that there had been some preliminary findings and research, but no detail work that I was able to find.
Man.
But one of the other components too is and this is not specific necessarily to the hippocampus. The example I'm going to bring up is, but there, it's something I find fascinating is the abundance of different receptor types within different brain regions, and the implication that has. For example, the D3 dopamine receptors are, to my knowledge, are primarily found within the hippocampus, and they're less common than the other receptors on the brain as a whole, but they're primarily found in the hippocampus. And one of the key differences between the D3 receptors and the D2 receptors, because I believe the D3 are D2-like, is that the D3 has a higher saturation threshold. And so the point at which it reaches saturation is a lot higher than within other areas such as the cortex, which begs the question, why? And what is that higher saturation threshold, or maximum saturation point, about? And is it that there needs to be differing levels of changes within the hippocampus as opposed to the cortex? Is it that there is feature extraction going on, so we already kind of know the information that we're dealing with, and once we store it, we really need to encode it quickly? Or like, or is it is the D3 as a result of needing to encode memories to later be processed. So we have to quickly encode them on the top layers of the hippocampus, so what is that? That's kind of one of the interesting, I need to do further research to find the answer, but like that does fascinate me, is like why there are those different receptor types that are prominently in one region over others. And what implication that has for that region,
I mean, to me, it seems like it has an element of wanting to minimize uncertainty by being able to understand as much information as possible so that it can find the most relevant experiences for it to be processed in the cortex. And so it's almost as if it's like checking to make sure, even if the information is very saturated, it makes it almost easier to find the specific points or information that it needs to relate to in a more broader sense. That's obviously I don't exactly know. That's just partly my hypothesis. I wish there was more like research into it.
Yeah, what was I gonna say? I'm blanking right now on, is it D1 that's stimulatory or D2? You remember?
I think it's D2.
D2?
Yeah.
Okay. Because D3s are D2 like, which means it's working on a stimulatory level, not a suppressive level. And D3s are commonly used in attention. That's one of their primary components. It's actually another thing that is interesting to me is, and I actually wasn't even aware of this until recently because I'd never heard of it. Which I guess shows you how much we've got going on in the brain. The fact that I was able to take a course on medical neuroscience and then not come across this information.
No, seriously.
But there are these things called receptor heteromers that basically are a synapse that combines two different receptor types. And so you can have D1 and D2s within the same synapse, and you can have D2s and D3s within the same synapse. And as a result, that can lead to some really complex interactions with dopamine.
Yeah.
So for some reason, I guess because I'd never come across this term before, I was under the impression that a synapse had within, let's like say dopamine or serotonin within its neurochemical type, it was limited to one receptor type. And come to find out, they can actually form these things called heteromers, which are basically the combination of multiple receptor types. So that's not always the case, that it's just one.
Yeah. And it needs both of those to be released.
Well, it would have different interactions with them because you'd have one that would fire, at certain levels and given certain conditions within the synapse. Or sorry, you'd have one receptor that would bind and cause, maybe larger changes downstream given certain conditions. than the other, but given another set of conditions, you might have the other receptor primarily be making the downstream changes.
Yeah. I actually think that might depend on the D1 receptors that modulate the D2 receptors, essentially.
Well, I mean, you can have D1 and D2 heteromers, and then you can have D2 and D3 heteromers as well. And you can have a combination of both of those that kind of interchangeably like play off of each other given different sets of conditions, you know, which to me adds a whole new layer of complexity to those synapses and neurons.
I know. I can barely even think about that. It's I mean, I can. It's just
hard enough to like contemplate the downstream changes that a single synapse type would have.
I know.
And you can start combining multiple that just take over given different conditions, you know, and
even within like a couple, even like with 100 neurons that are able to do that, that seems very complicated to navigate how it does. Well,
given a single neuron, that seems difficult to calculate.
Hundreds of millions of years of evolution, thankfully, have been able to
barely tapped the vastness of human potential.
Yes, indeed.
Spider-Man quote.
Yeah. So
cool.
Hippocampus.
Dude, that is awesome. The hippocampus is one of those areas that I've always found very fascinating.
Oh my goodness. It's insane.
Like I love my cortex, don't get me wrong. I love a good cortex. Cortexes are great. But my hippocampus, man.
I mean, hey, the cortex wouldn't be able to work without the hippocampus.
True. Yeah. Without the hippocampus, it's we're basically no better than an insect, kind of. Like we probably less good than an insect. We'd only be able to deal with immediate variables.
Even to a very small degree. Like we might be able to do things that are coded within our genetics, like eat, sleep. We might be able to utilize the basal ganglia and cerebellum to learn how to walk and to balance those specific things. But any further complication,
any sort of context would be impossible.
Because, you know, we're 20% genetics, 80% experience.
Yeah.
And that's how we grow. And if those new synapses aren't able to learn from the experience and then through memory encoding consolidation, use it at later points once it processes in the cortex, you couldn't do anything. There's no complicated decisions you could make.
Yeah. No sort of informed decision would be possible.
And that was first found out in the most famous case study of the hippocampus with the patient HM who had a partial lobotomy that removed his hippocampus because he was having seizures. And they decided to remove the area, the hippocampus, that had these seizures. And what happened was that it was actually very interesting. His intelligence, his IQ went up. And so he had some very benefits. He also stopped having seizures. But one of the main things they noticed is that he was unable to learn anything new. Nothing else was able to be learned. And that had major implications for the time. It finally unveiled kind of mysteries behind memory and being able to form memories. And so, more of the story is, don't get a partial lobotomy.
Well, you heard it here first, guys. Do you want to go to break and then we can continue after that?
Let's do it.
All righty. Well, guys, let me see if I can do this from my phone because that would be a whole lot easier. We will, after our break, we are going to go over a nootropic topic, which is Oxiracetam again. And then we will probably just have a free flow section for a bit and talk about whatever's been bugging us, which I know there's something in particular that I wanted to hear your thoughts on because it bothers me for some reason. And so
sweet.
Yeah, you'll get to figure out what's been bothering me. And we will see you guys then, supposing this works. If not, we'll see you still. You want to check if it worked?
Is the auto director on?
Did it switch back? Let's. Oh, it's like it heard me because the auto director switched itself back on for some reason. Well, good thing it did it. What?
It just sounds really
Yeah, it does. Okay, well, welcome back, guys.
Oh, yes, we are back. All right, now it's time to go over Oxiracetam.
Yes,
all right.
indeed.
Yes. So one of the main things that Oxiracetam was used for was to help improve cognitive impairments, but it also has wonderful benefits as well for people who are completely healthy. And there was some vascular cognitive impairment studies that were multicenter randomized, double-blind, placebo-controlled trials with 500 patients, and they each had 800 milligrams of oxiracetam or placebo twice daily for 36 weeks. And do you know the results of that study?
For the which one?
For the vascular cognitive impairment study.
I noticed too that it did not include it because the with that study there weren't any results posted that I found.
Interesting.
So that was something that I was thinking about, like, do I even include this like in the report, because it's not getting any results information. However, it does give context that this has been researched and how it was researched and whatnot.
And if we were guessing, if we look at the vascular dementia rat study, we can see that they used a surgical procedure to induce vascular dementia that restricts blood flow to the brain, and oxiracetam alleviated a lot of the learning and memory deficits, as well as it improved your neurons that were previously damaged. So I would guess that the results are somewhat similar to the rat study.
Which one were you talking about just there? Sorry, I was working on getting the auto director set
The
up.
vascular dementia rat study.
Oh yeah, yep.
Fairly similar.
And they did incorporate. You talk about the Morris water maze test there that they did.
Oh, yeah, mention that.
So they did a Morris water maze test, which was a behavioral test that's used to assess spatial learning and memory with rats and rodents. And they also performed and I don't know how to, honestly, I don't know how to say this word. I think it's nizzle, but I'm not sure. Nizzle staining, and it's basically a technique that's used to visualize the neuron cell bodies.
Yeah.
But they found that it improved not only spatial learning and reversed those neuropathological changes in the hippocampus CA1 region, and which happens to be a region that is, interestingly enough, considering our recent discussion of the hippocampus, as crucial for spatial memory and memory consolidation. So, kind of like you were talking about with that whole spatial navigation component, you know, this seems to almost be confirming and validating that information. Now, they did do an Alzheimer's disease study for the neuroprotective elements of oxiracetam, or potential neuroprotective elements of oxiracetam. And they found that oxiracetam suppressed microglial activation and inflammation. The BV2 cells, which are a type of microglial cell, immune cells in the brain that were used in the research. They reduced the inflammatory molecule production. They protected the HT22 cells from toxicity. Also, they found that oxiracetam lessens the effects of electroshock treatment and damage in animals, and prevents decreased acetylcholine levels. And now that part is key. Kind of one of those key findings, because that looks to be one of its mechanisms of action that's through its modulation, and specifically the modulation of the acetylcholine receptors. It enhances the acetylcholine release, and in addition to that, prevents reuptake of acetylcholine, leading to higher levels of acetylcholine in a synapse.
Yeah.
It also appears to interact with the glutamate receptors, prevents amnesia associated with acetylcholine synapse inhibition. So inhibition of acetylcholine synthesis. And so that would suggest that it is able to prompt the creation and release of acetylcholine into the synapse, as well as preventing the reuptake. And enhances the precholinergic functions without affecting the acetylcholine activity, or the acetylcholine enzymatic breakdown activity, sorry. So oxiracetam doesn't affect that particular enzyme, suggesting that it has a different mechanism.
Yeah. And it also enhances synaptic plasticity, which is
through that. I'd imagine the enhanced acetylcholine release and maintenance within the synapse. I would imagine that would lead to an increase in synaptic plasticity, considering that's one of the main components there.
As well as AMPA receptor modulation that's involved in synaptic
as a result, right?
Yeah, as a result, involves in synaptic transmission and plasticity. And it's also interesting because that increases brain energy metabolism and ATP synthesis.
That's one of the things I find kind of super fascinating about the this, because like the other racetams all in some form or another interact with the acetylcholine receptors. You know, they will stimulate the release or prevent the reuptake. And by the way, just as a FYI, I'm just now realizing that people might not know this, and it might seem contradictory. Reuptake is different from enzymatic breakdown.
Yeah.
Of a neurochemical. When a neurochemical is released into a synapse, it can be removed from the synapse through a variety of methods. One of them is reuptake, where the synapse that released it reuptakes the neurochemical and reabsorbs it. Another one is through enzymatic breakdown, which is where an enzyme that is able to break down that component is released and it starts degrading it. Another one is diffusion, where that neurochemical gets diffused outside of the synapse and gets sometimes absorbed by other synapses, leading to regional effects. And so there are multiple methods. So that's not contrary there, the fact that it prevents reuptake, but also doesn't affect the enzymatic breakdown activity.
Yes.
But anyway, back to what I was saying. The effect on ATP is interesting, because that's not one that I've seen as a common component of the racetams. That's almost like the kind of element there that feels like it makes it unique.
That's something. It's on kind of
right
way it stands out. Why
for those that don't know, ATP is the like essential. It's a component of life. It's like the primary energy that cells use.
Very vital.
So by by increasing the synthesis, as we age, our ATP synthesis typically declines, and which leads to a lot of different outcroppings and problems as a result, and decreased body function.
Yeah.
And all that kind of stuff. So by increasing ATP synthesis, we are essentially fighting a lot of that degradation that happens.
It's almost like oh shoot, I forgot which nootropic it was, but it's one that takes the genetic structure of the cell and recodes its primary state. And I think this is somewhat similar to where it is increasing ATP by reverting it back to its prime state of production, which I think is, that's so important, especially when it just comes to a healthy brain and being able to function properly and continue to enhance and learn and develop new connections. Because if you don't have any good neurons, connections aren't going to work as well as you want it to.
I've got all bad neurons.
Bad neurons.
They're very bad neurons.
Got 100 billion neurons. Not a single one is good.
Naughty. Sorry.
Naughty neurons.
Naughty neuron.
Seriously. Okay, so
so let's see. We've got the ATP increase. Here we've got the acetylcholine release and reuptake prevention within the synapse that's happening, leading to higher levels of synaptic plasticity there. And it apparently also decreases abnormal glucose and citric acid accumulation as well. And thereby kind of protects the brain and provides that neuroprotective component and increases ATP metabolism as well. And so beyond just those benefits there, it also has been obviously researched, and specifically for Alzheimer's is where they were exploring this. It researched the neuroprotective component because it looks like that it can protect neurons from oxidative stress, which is probably where it gets its name from. But it can protect neurons from oxidative stress and excitotoxicity, and also prevents the excessive stimulation of neurons by neurotransmitters, which would lead to excitotoxicity, which would then lead to excessive cell damage and then death. Of those cells. And so
that's a good thing to avoid.
Yeah, we want to avoid that at all costs. And it looks like Oxiracetam can help with that. So I could see that being potentially useful for applications such as, okay, you are taking this, medication that maybe has an excitatory effect on neurons, but could potentially lead to undesired long-term results as a result of overexcitation of that neuron. Maybe you take something like Oxiracetam in addition to it to help protect it and prevent it from accumulating damage as quickly.
Yeah, for sure. So
we want to go over the brain regions real fast that it interacts with.
So we've talked about kind of the receptors, but and a little bit of the brain regions, but let's talk about it a little more. So, that it interacts with the hippocampus, obviously the cortex, the cerebral cortex, as well as the striatum. So the striatum, it's a pretty crucial component of the motor and reward systems. It also interacts with the septum pellucidum, which is a thin membrane in the brain that separates the lateral ventricles, which has found to have the highest brain concentrations of oxiracetam. So this seems to be kind of where it's kind of made a hub of interactions, which is really cool. And so, and when we talk about the hippocampus, we can see that it actually interacts with the CA1 and the CA3, as well as the dentate gyrus. Also, hold on, wait. Really fun fact that I forgot to mention about the hippocampus. What does CA mean? cornu-ammonis. Okay. And cornu-ammonis.
Is it cornu-ammonis?
Cornu-ammonis.
Okay.
Yeah. Which was named after one of the ancient Egyptian gods that had horn-like features. And so they used that as reference to name the hippocampus that
Interesting.
has a horn-like
Yeah.
structure, which is, I think it's really cool.
That is
Little
cool.
fun fact. But yeah, so it's interacting with CA1, CA3, as well as the dentate gyrus, which is really good for producing new neurons, neurogenesis, as well as being able to separate similar experiences. So it's able to differentiate between, let's say you park a car one day in this specific place in a parking lot. The next day, you do a different one. Those two are very similar experiences. And sometimes we'll have issue with remembering, wait, did today I park here or today did I park here? The dentate gyrus says it's help separate those two. I think it's really cool and very important.
So temporal difference.
Mm-hmm.
Nice.
Yep. Memory separation. And then the interaction with the prefrontal cortex, the parietal cortex, and the temporal cortex. It's interacting with a lot of the very important regions of the brain and has various effects on, like brain networks, and is pretty awesome. So those are kind of like the things that it interacts with, kind of the substance of chemical.
So, interestingly, this is actually one of the most common studies I think you come across when you research studies on oxiracetam, but how high altitude can decrease cognitive function, right? So there's actually been evidence to suggest that oxiracetam may improve cognition at high altitudes, which is interesting. I don't know exactly what mechanism that would be that would cause that, but that is a very common thing I came across. So the specific way in which that was measured was through enhanced EEG power spectral entropy at 4,000 meters altitude. Obviously you have the alleviated anti-inflammatory activity on brain network regions that are inflamed, as well as, interestingly, the potential ameliorated cognitive impairment in early phase traumatic brain injury. So this could be something that could be useful for people dealing with TBI or TBI related issues that pop up. And to me, it's just so cool that there are things out there that can help the brain repair itself from injury. Like somebody gets traumatic brain injury, like most people think of that as like, oh, the brain, like, well, it's injured, like that's it for that part of the brain. It's but like the brain can heal itself.
Yeah, and it can also adapt. So even if maybe the damaged neurons die off, if
they can rewire themselves, maybe.
Exactly. And this actually helps with enhanced reconnectivity within those specific functions that you need. So if you are still doing the tasks that need that working networks, it is going to reintegrate itself back into the brain, which I think is really awesome. And it might even, well, I'm not going to say that, but using the dentate gyrus, it might create very specialized neurons for those tasks. And that might also have some very interesting effects on your experience of what you need to do.
Yeah.
Which is pretty cool.
So the as far as side effects and whatnot for this one, as with the majority of the racetams, it's pretty well tolerated. There's not many side effects. The most common one that you'll come across with the racetams is going to be the headaches. It's referred to as your choline headaches, which basically is your brain indicating to you that you don't have enough resources to make the acetylcholine that you're asking for there. And so basically the way to resolve that is to take a choline supplement along with or before the racetam to make sure that your body has enough resources to make that. And once you do that, these other choline headaches go away. I could say that one from a personal experience. I've definitely ran into that before, and just choline supplementation fixes it right up. Typically like 500 milligrams to 1,000 milligrams a day of either alpha GPC or what is that other one called? I don't know. I remember it's patented, like there's a patented name brand version that's commonly used, but it's a little more bioavailable.
Oh, nice. Yeah.
But
yeah. So overall, it's a very promising nootropic, I think, with various potential cognitive enhancing effects and modulates neurotransmitters, enhances synaptic plasticity, and improves energy in the brain, ATP, as well as it protects the brain, which is very awesome. And it affects all of the key brain regions it needs for cognition. So it has that enhancement aspect to it. And currently, there is very limited research in it.
As with most of the racetams, most of the research has been done in Russia, and is gone relatively unexplored. Although that stuff is available in Russia, like as just common like over-the-counter stuff, like it's gone unexplored here mainly because of our medical system and the fact that it's so freaking expensive to get stuff approved and researched.
Seriously. But yeah, overall, it's pretty awesome.
Nice.
Yes, pretty awesome. So it is 12. It's getting late.
Cool.
So thank you guys for watching this podcast. We really appreciate it. This one was a really fun one for us. We got to talk about.
But they didn't get to hear what was distressing me.
Maybe we should have started a little sooner. I have to go home, but it's fine.
Next time, you'll get to hear what's distressing me.
Yes. So tune in, and it'll be a good one. That's for sure.
Oh yeah, as usual. And thank you guys so much for watching. Appreciate you guys. See here if I can even just close down the dang connection here.
The daggum
thing. Need a better way of stopping this. Alrighty, guys. Well, thank you again for watching.
Yes.
And we will hopefully see you guys next week on Tuesday. If not before then, we're thinking about posting some individual stuff and doing maybe some live streams of me coding. And so you guys can talk to us or ask about any questions you have about that. And then he's maybe thinking about doing some vlogging or something.
Yes, we're gonna do some vlogs as I continue to learn with machine learning. You guys can learn along with me as well as watch Ryan code. So a lot of new opportunities for you to learn new things like coding, as well as come on this journey of machine learning, as well as anything else that fascinates me that I want to look into the details in. So join us for that.
Cool.
Great.
Alrighty. Well, thank you guys. See you next week. And as always, keep it real and tune in.
Riding that thing.
I couldn't remember what as always we said. So, oh well.
Perfect.
All right. Later, guys.
Yeah.